Ever wonder about the invisible forces that are right now holding our world together? I mean, they're everywhere. They're in the bridge you drive across, the phone in your hand, even the chair you're sitting in. Well, today, we're going to make those hidden forces visible.
Okay, so this sounds a bit like the start of a riddle, right? You've got a heavy-duty industrial gear, a massive steel and concrete bridge, and this tiny little piece of tech on your wrist. What on earth could possibly connect all three?
And the answer is stress analysis. Yep, it's this hidden science that's behind the safety, the strength, and the efficiency of, well, pretty much everything around us. So let's dive in and see what that really means.
All right, so what exactly is this invisible push and pull we're talking about? Now, I know stress analysis sounds super technical, but the core idea is something you actually feel all the time.
Think about this. Grab a rubber band and just slowly stretch it. You can feel that tension building up inside it, right? That feeling? That's stress. And if you pull just a little too hard, snap. Stress analysis is basically the science of calculating exactly where and when that snap is going to happen for anything and everything, from an airplane wing to a tiny little engine part.
Now, to figure this out, engineers don't just, guess. They use these incredibly powerful computer simulations. One of the main ones is called finite element analysis, or FEA. What it does, in a nutshell, is it takes a digital object and breaks it down into thousands, sometimes millions, of tiny little digital blocks. By calculating the forces on every single one of those blocks, they can see exactly how the whole thing is going to act under pressure. It's like having a digital twin of an object that they can test to destruction, all before a single piece of metal is ever cut.
And that ability, the power to predict failure before it happens, is what lets us build a safer, more reliable world. So let's see how this goes from just a theory on a computer to the actual things that we use every single day.
I mean, this is the big question for any engineer, isn't it? How do you design something that you know isn't going to break, especially when it's under intense pressure, moving at high speed, or carrying a huge amount of weight? And the answer, as you've probably figured out by now, is all about that stress analysis.
What's so amazing to me is just how wide-ranging this is. It works on every possible scale. We're talking about the huge pressures inside a giant storage tank and the intense centrifugal force in a tiny motor inside a wheel. It helps design the springs for robots that climb wind turbines, it makes sure a trampoline is safe for everyone to jump on, and it calculates exactly how a cell tower will hold up in a storm. This science is, quite literally, everywhere.
And this just lays it out so clearly. Before we had these powerful tools, a lot of engineering was about overbuilding, just making things extra heavy just in case, and honestly, a lot of guesswork. But now, failure points aren't a surprise. They're predicted. Designs can be lean, lightweight, and strong. Safety is no longer a guess. It is engineered.
But here's the thing. Stress isn't just about outside forces like wind and weight. Sometimes the biggest and most important battles are happening deep down inside the materials themselves, on a totally microscopic level.
Right, because stress can actually be baked into a material from the moment it's made. Think about 3D printed metals or some of these super advanced composite materials. The very process of creating them can build in these hidden internal forces that could cause them to fail way down the line unless you know they're there and design for them.
So how in the world do you see something that's invisible and locked inside a solid chunk of steel? Well, scientists use these amazing techniques like something called X-ray diffractometry. Basically, they shoot a beam of X-rays at the material, and then they watch how those X-rays bounce back. Tiny, almost imperceptible changes in that bounce-back pattern tell them that the atoms inside are being squeezed or stretched, and from that, they can calculate the exact amount of hidden stress. It's wild.
And this is where it gets really, really powerful. By digging into these internal forces, engineers solve these incredibly complex puzzles. Got fire-damaged concrete? They can analyze it to see if the building is still safe. Worried about adhesives failing in a composite part? They can study the stress right at that boundary layer. They can even predict the exact lifespan of a 3D printed part before it cracks from fatigue. It's like giving the material itself a complete health checkup.
Okay, so for decades, this has been the world of stress analysis, right? Concrete, steel, machines. But right now, there is a revolution happening, and it is being powered by artificial intelligence and is taking this science into a totally unexpected, brand new place.
For the longest time, the whole game was mechanical. The big question was always, at what exact point does this steel beam buckle? When is this gear tooth going to shear right off? It was all about the physical limits of stuff.
But what happens when the material you're analyzing isn't steel, but a person? That's right. The exact same ideas, finding patterns, measuring strain, predicting breaking points, are now being applied to us. The study of mechanical stress is becoming the study of human stress.
So get this, the same fundamental thinking is being used in totally new ways. A machine learning model that gets trained to predict a stress hotspot in a complicated gear is now being mirrored by a model that looks at data from your smartwatch to figure out your personal stress levels. Algorithms are being built to predict stress patterns in really demanding jobs, just like they predict fatigue in an airplane part.
And whether we're talking about a machine or a person, the goal is the same. Find that critical breaking point before it's too late. So take this number, 62%. What does that even mean? Well, it represents the exact kind of critical point of failure that this whole science is designed to find.
That 62%, that was the measured stress increase in a vital machine part every time it got hit with an impact. Finding that one little hotspot, that 62% spike, is what prevents the entire machine from a catastrophic failure. And that is the core idea, whether that hotspot is in a steel coupling or in a person's workday.
You know, it really gets to the heart of everything we've been talking about. Whether we're talking about the physical stress in a bridge or the psychological stress measured by a smartwatch, this field at its core is about understanding the forces that challenge stability and then figuring out how to build resilience against them.
Which kind of leaves us with this one big, fascinating thought to chew on. As our technology gets better and better at predicting every single breaking point in our machines and now in ourselves, the really important question becomes one of choice. What will we focus this incredible power on? What amazing new things will we feel safe enough to build? And maybe more importantly, what or who will we decide is most important to protect from ever reaching that breaking point?